So in the previous class, we started with the first chapter. We have seen basic assumptions which we use throughout this subject and started with the first chapter. In the first chapter, we studied with basic definitions of stress, strain, different types of stresses, different types of strains, conventional stress, conventional strain, and later we have seen the stress strain curve of ductile materials and brittle materials in both tension and shear. So we have observed very importantly that the main difference between the primary difference between a ductile material and brittle material is basically plastic deformation. If a material can undergo plastic deformation before fracture, it means it is a ductile material. If a material cannot undergo plastic deformation before fracture, it should be called as a brittle material. And later we have seen the definition of failure, definition of strength and all, and we have understood that the ductile materials fail by yielding and brittle materials fail by fracture. Okay, so we should be keeping in mind that though ductile materials won't experience fracture at the phenomenon of yielding, still we discard them and take that failure has happened. So we should be very careful. Only in brittle materials we will wait till fracture to happen. Okay, and we also seen a couple of things that when you are releasing the load from plastic region, from the start of plastic region, that is after point C, after yield point, you will be regaining some amount of strain, but not complete amount of strain. So remaining amount of strain will be left over. Okay, so some amount of permanent strain will be left over on the material. Now from that condition, if you again load it, you will observe that the yield point will increase. Okay, so this is a phenomena from point C. So whether you do in the plastic region or you do in the strain hardening region or necking region, this is a phenomena there. So you'll be having higher value of yield point. Clear? So this is used in manufacturing metal forming operations, because if you do plastic deformation by metal forming operations, so we are increasing its yield point. So at a microstructure level or at a microscopic level, what happening is the defects, everything are getting closed up, and that is giving rise to increase of yield point. So as far as our SOM subject is concerned, we are concerned about only increasing the value of yield point. Okay, I mean, we are concerned about the output itself. We are not concerned about how it actually has happened. So we'll study those things in the subject of metal science or manufacturing engineering. Now, can anybody give me the answer for this question? I hope I have given this question as a homework. Okay, let's look into this question. It's given that consider the stress strain curve of an ideal elastic plastic strain hardening material as shown in the figure. The metal was loaded in uniaxial tension starting from O. Upon loading, the stress strain curve passes through initial yield point at P and then strain hardens to point Q. So initial yield point of P means, so P is the yield point, and after P plastic deformation starts. So so they are saying the strain hardening has happened to point Q. So they mean that as we are approaching from point P to point Q, slope of the curve is non-zero. So nowhere slope is actually equal to 0. Where the load was stopped, from the point Q, the specimen was unloaded to point R. So where the stress is 0. If the same specimen is reloaded in tension from point R, the value of stress at which the material yields again is. So here, if you observe, your correct answer should be, it should be more than 180 megapascal. So before, when it was unloaded, when there was no loading at all, no deformation at all, so yield point or the strength of the material was 180 megapascal. Now we have created stress or deformed beyond this point, and then we have unloaded. Now if you again load it, the strength will come more than 180 megapascal, and here we see that the curve is going till point Q. So we can simply say yielding happens at point Q, that is 210 megapascal. So the correct answer is 210 megapascal itself. Roshan, you have thought partially, whatever you thought partially is right only, but ultimately your answer is wrong. So the value of yield point should be more than 180 megapascal, and here from the graph we don't have any other number to tell, so you can say it will be 210 megapascal. Clear? That is the answer for this question. This question is about making you people to think about Hooke's law. That's why I kept this as a question here, and it's a previous IAS question as well. The correct answer is actually B, proportionality limit or limit of proportionality. Why it is, I would like to explain you by giving the history of Hooke's law or complete explanation of Hooke's law. from which you'll understand why it is valid up to limit of proportionality only. Okay, and regarding this, there is a huge confusion in many textbooks as well, between many authors as well, many faculties as well. But the correct answer for this one is limit of proportionality. So why? You can understand from the explanation part. Hooke's law came into existence when spring and force system were used. Spring and force system were used. So when spring and force system were used, it was very clear that force was proportional to elongation. That means if you increase the value of force by some value, some factor, elongation is also increased by the same factor. That means if you are doubling the force, elongation is being doubled. If you are tripling the force, elongation is also being tripled there. Okay, so it was observed there. Understand? Same behavior was also observed when the solids are deforming elastically. So if you take this force as P, so elongation produced is proportional to the applied force P. Understand? Elongation produced is proportional to applied force P. So here if you remove the constants, if you remove all the constants, you will understand that you can write down as stress proportional to strain. How it will come? If you write down force as stress into area of cross section and elongation as strain into length. So area and length you can cancel out because they are constants, because we always take initial values or conventional values. So you will get stress proportional to strain. So strictly speaking, this is the Hooke's law. Strictly speaking, this is a Hooke's law. Okay. So we use this one also. Okay. So but still till now there is no strict statement or strict any question where it was asked whether this is the correct Hooke's law or this is the correct Hooke's law. So correctly speaking, the better answer is P proportional to delta. Next better answer is sigma proportional to strain. But anyways, till now no question came in such a way at that level. So you can consider both the equations are same only. So Hooke's law can be denoted by load proportional to elongation and stress proportional to strain. So here we see in Hooke's law, if you write down stress proportional to strain, epsilon power 1 is coming. So stress and strain should be linearly proportional. So if you observe stress strain curve in tension, because we are dealing with linear stress and linear strain, normal stress and normal strain only. So it is a straight line till the proportionality limits. After proportionality limit, elastic limit will come, yield point will come. So where this proportionality or straight line phenomena is not maintained. So this Hooke's law is valid up to only proportionality limits. Understand? Clear? So you guys can copy. Once you are done copying, I will tell you one very important point, because there are few conditions where Hooke's law is not valid. So we study them, but we always forget. We never ever cross think whether Hooke's law is valid or not. So we are going to look into that case. So kindly copy this and please let me know. Kindly be a little fast in copying. Don't be a little slow. We can save the time for solving the numericals. So it's done. Others also. Okay. So please remember that this Hooke's law is valid when this stress and strain are produced by mechanical means. That means the stress and strain should be produced by either forces or pressures. That's all. If stresses or strains are produced by any other means like thermal means, increasing temperature, etc., there you can't expect Hooke's law to be valid. Okay. For example, you take a free rod heated to expand. There you're going to see strain is always non-zero, but stress is always zero. Due to change of temperature, strain will be going on produced, but stress will never ever get produced. Stress will always be zero there. Okay. So strain is going on increased, but stress is always zero. So you can't say proportionality is valid there. So please remember, this Hooke's law is valid. This Hooke's law is valid only for mechanical cases of stress and strain. Okay. So I would like to first of all explain you the difference between measuring and calculating. So measuring means you will be getting that value directly from the readings. For example, you take density. You take density of material. Understand? Okay. So fine. That's what. Let's say volume. So if you are not even volume also. For example, you have a cuboid and you'd like to measure the value of length. So you always say we measure the value of length. We don't say we calculate the value of length, because you will be using some setup, or you'll be using some instrument which will be giving you that reading directly. So using the value of length, breadth, height which are measured, you will be calculating volume. Understand? Okay, and if you use a weighing machine, you'll be measuring the value of mass. Okay, so you will not calculate mass, you'll be measuring the value of mass. So once you measure mass, once you measure the value of dimensions, so using mass you can get the value of something, you can calculate some other values. Using length, breadth and height, you can calculate the value of volumes. So I hope you people are very much clear. So the readings which you can directly get from the instruments are actually called as measurements, or those should be called as measured values, and whichever you get by using a formula, they should be called as calculated. So here if you see, in the simple tension test, we actually measure load and elongation. So the dial gauge will be giving you the applied load value, and the extensometer will give you the value of the elongation. Understand? So using the value of applied load dividing by original area, you will calculate the value of engineering stress, dividing the elongation, measured elongation dividing by original length, you will be getting the value of engineering strain. So engineering stress and engineering strain are calculated values. Okay, in the same way, using engineering stress and engineering strain, you can you can again calculate true stress and true strain. Okay, and also after drawing conventional stress, conventional strain graph, you can again calculate the value of Young's modulus, because that is the slope of the curve up to proportional limit, which we're going to study a little later. So if you take any value like Point's ratio, Young's modulus, true stress, true strain, engineering stress, engineering strain, all are calculated values. Okay, the measured values are only load and elongation. Kindly remember this thing here. Okay, everybody, you can write down the statement. In a simple tension test, load and elongation are measured and remaining all the other values are calculated. So these are the primary two values which you're going to get from instruments. Using them, you can get any other value. Okay, let's go ahead with the next terms, elasticity and ductility. Kindly copy first of all. After that, I will go ahead with explaining. So elasticity, ductility are opposite. Elasticity and plasticity are opposite to each other, and plasticity decides the ductility phenomena. So elasticity is given the name as, or it is nothing but, so the property of the material, once you release the load, it should be able to regain its original shape and dimensions. So plasticity means not able to regain its original shape and dimensions. Now, if ductility is to be defined, it is completely based upon plasticity. So how well the material can undergo plastic deformation before fracture. So for example, you take two rubber bands. Okay, so one rubber band can undergo, let's assume, plastic deformation up to this amount of length before fracture. So once you stretch up to this length, it will undergo fracture, let's assume, or it will undergo breakage. But other rubber band will undergo elongation up to this level or this amount of elongation before undergoing fracture or before undergoing breakage. So the second one is more ductile than the other. Okay, so the ductility is completely based upon the plasticity behavior. So ductility is the ability of the material to change its shape and dimensions plastically before fracture. Okay.